Pursuit-evasion is a family of problems in mathematics and computer science in which one group attempts to track down members of another group in an environment. Early work on problems of this type modeled the environment geometrically. In 1976, Torrance Parsons introduced a formulation whereby movement is constrained by a graph. The geometric formulation is sometimes called continuous pursuit evasion, and the graph formulation discrete pursuit evasion. Current research is typically limited to one of these two formulations. Discrete formulation. In the discrete formulation of the pursuit evasion problem, the environment is modeled as a graph. Problem definition: there are innumerable possible variants of pursuit evasion, though they tend to share many elements. A typical, basic example is as follows. Pursuers and evaders occupy nodes of a graph. The two sides take alternate turns, which consist of each member either staying put or moving along an edge to an adjacent node. If a pursuer occupies the same node as an evader, the evader is captured and removed from the graph. The question usually posed is how many pursuers are necessary to ensure the eventual capture of all the evaders. If one pursuer suffices, then a single evader can always be captured in time linear to the number of n nodes of the graph. Capturing r evaders with k pursuers can take in the order of Rn time as well, but the exact bounds for more than one pursuer are still unknown. Often the movement rules are altered by changing the velocity of the evaders. This velocity is the maximum number of edges that an evader can move along in a single turn. In the example above, the evaders have a velocity of 1. At the other extreme is the concept of infinite velocity, which allows an evader to move to any node in the graph so long as there is a path between its original and final positions that contains no nodes occupied by a pursuer. Similarly, some variants arm the pursuers with helicopters, which allow them to move to any vertex on their turn. Other variants ignore the restriction that pursuers and evaders must always occupy a node and allow for the possibility that they are positioned somewhere along an edge. These variants are often referred to as sweeping problems, whilst the previous variants would fall under the category of searching problems. Several variants are equivalent to important graph parameters. Specifically, finding the number of pursuers necessary to capture a single evader with infinite velocity in a graph G is equivalent to finding the tree width of G, and a winning strategy for the evader may be described in terms of a haven in G. If this evader is invisible to the pursuers, then the problem is equivalent to finding the path width or vertex separation. Finding the number of pursuers necessary to capture a single invisible evader in a graph G in a single turn is equivalent to finding the size of the minimum dominating set of G. Assuming the pursuers can initially deploy wherever they like, the board game Scotland Yard is a variant of the pursuit evasion problem. Complexity: the complexity of several pursuit evasion variants, namely how many pursuers are needed to clear a given graph and how a given number of pursuers should move on the graph to clear it with either a minimum sum of their travel distances or minimum task completion time, has been studied by Nimrod Megiddo, L. Hakimi, Michael R. Gary, David S. Johnson, and Christos H. Papadimitriou, and R. Bori, Tovey and S. Koenig. Multiplayer pursuit evasion games. Solving multiplayer pursuit evasion games has also received increased attention. C.R. Vidal al. Chungnan Furukawa, Hespana al. And the references therein. Marcos A. M. Vieira and Ramesh Govindan and Gaurav S. Sukatma provided an algorithm that computes the minimal completion time strategy for pursuers to capture all evaders when all players make optimal decisions based on complete knowledge. This algorithm can also be applied to when evader is significantly faster than pursuers. Unfortunately, these algorithms do not scale beyond a small number of robots. To overcome this problem, Marcos A. M. Vieira and Ramesh Govindan and Gaurav S. Sukatma design and implement a partition algorithm where pursuers capture evaders by decomposing the game into multiple multi-pursuer single evader games. Continuous formulation. In the continuous formulation of pursuit-evasion games, the environment is modeled geometrically, typically taking the form of the Euclidean plane or another manifold. Variants of the game may impose maneuverability constraints on the players, such as a limited range of speed or acceleration. Obstacles may also be used. Applications. One of the initial applications of the pursuit-evasion problem was missile guidance systems formulated by Rufus Isaacs at the RAND Corporation.